So I'm going to be going over Stokes' theorem example, and these are the notes by Ekin Yelkin, and I'm Nathan, and I'm going to be presenting them. So first is an example, and we need to graph the hemisphere by surface S given by the equation x squared plus y squared plus z squared equals 25. Now normally that would be a sphere, but because it's above the x-axis, that's where x is greater than or equal to 0, we have the hemisphere with a normal vector in the direction of the positive x-axis. And then we have the vector field f, where it belongs to x cubed, 0, and y. So the graph of that sphere looks like what we have here. And you can see that the circular region is in the YZ plane. It looks like it's cut out of a sphere here, and it goes up towards in the x-axis direction. You can see the normal vector there as well. So, first part of the question is show whether the vector field F is conservative. So there's a few methods we can use to show if a vector field is conservative. First, we can use gradient theorem to show if it's conservative and see if there's a potential function of lowercase f in which the gradient of f, that is lowercase function of f, is equal to our vector field. So if we can find a function f and its gradient is equal to our vector field, we know that it's a conservative vector field. The second method is take the integral of our vector field, and that would be a curvature around C, that is region C, must be 0. So there must be no circulation around a closed curve. If that is true, if there's no circulation, then f is conservative. Next, in 3D space, we can use the notation of a curl of f, and if the curl of f is 0, then it's a conservative vector field. Now this builds on gradient theorem, but if the cross product of the curl the curl of f, that is the cross product of the gradient to f, is 0, we know it's a conservative vector field. So that's what we're going to be using because it's the easiest computational method in this case. So that is the curl of f is equal to the gradient crossed with the vector field f. And if that's 0, we have a conservative vector field. So where f is given by p of I plus q and j and r and k, or in the coordinates notation, p, q, and r. And the gradient is the partial derivatives of each coordinate. You can see that here with the partial derivative of x and I, the partial derivative of y and j, and the partial derivative of z and k. Then the curl of f will be the cross product of the gradient and f, given by this equation here. So to solve this equation, we need to find the partial derivative of r and y, partial derivative of q and z, etc. So you can see the partial derivative of r and y is 1, partial derivative of q and z is 0, partial derivative of p and z is 0, partial derivative of r and x is 0, partial derivative of q and x is 0, and the partial derivative of p and y is 0. So when we compute that and plug that into this equation here, we actually see that it's 1 minus 0 in I, 0 minus 0 in j, and 0 minus 0 in k, which leaves us with the curl of f equal to 1. Now, as our definition from the first one, we know that the curl of f has to be 0 for conservative vector fields. Therefore, it's a non-conservative vector field. So f is not conservative. Next, we're going to evaluate the double integral of the cross product of the gradient with the vector field. And we're going to show what this equation equals to.